Okay, so now, oh, yes, sorry. Absolutely. So now we are going to deal with new base graphs. Pardon me? I think in those piles, if there's an extra one, grab it. And if not, then I don't have it. No, the other pile, sorry, keep going. Yeah, those ones. If there's one in there, grab it. And then bring the one from home and replace it. Perfect. Okay, so we're going to create two new base graphs. We are going to graph sine and we are going to graph cosine today. Now, the way we're going to graph it is quite literally based on the unit circle. Everything's based on the unit circle. The sine graph is based on the y points of the unit circle. So I've got this little video to kind of show you how they relate. So here's our unit circle. We are considering the y value that is created as the angle increases. So the angle is going to increase along the x value because the angles are our x, and it's going to graph the y value. So it's going to give you an idea of what we do. So you'll notice that the y's increase, and then the y's come back down, the y's become negative, and that after they reach the bottom, they increase back to 0. So in the unit circle, all we're doing is taking the y values around the unit circle and creating our sine graph. So everything that we do is based on the circle.
Is it important?
No, it's not. Okay, so first thing we need to understand is this is a periodic function. A periodic function is a function whose graph repeats regularly. So we did one rotation around the unit circle in that video, but could that terminal arm just keep spinning forever and ever and repeat the same pattern over and over and over again? That's what we're talking about when we talk about a periodic function. So using the information that we just saw from the unit circle, we're going to graph the sine graph. So quick little unit circle here. Let's start with 0 degrees. At the point 1, 0, the sine is the y value. So our y value is 0 at 0 degrees. I take a look at the different scale that I've got. So the next one I'm going to use is my pi over 4, which is root 2 over 2, root 2 over 2. Now, I need to figure out where to graph that. So in your graphing calculators, guys, give me a decimal value for what is root 2 over 2 divided by 2. What's the decimalized value? 0.71? Is that what you guys got? So at pi over 4, we're at 0.71. So we're more than halfway. This is not a line. This is a curve. When we get to pi over 2, so we're at the top, our y value is now at 1. I've reached the high point along the y. We go to our next value at 3 pi over 2. It's a negative there. And our y value goes back to root 2 over 2, which is our 0.7. Continue along. At pi, we've got that y value of 0. So when we think unit circle, my y's increased to 1 and then decreased back to 0. Now I'm dealing with my negative y's. So now when I'm at 5 pi over 4, I'm at negative 0.7. This is harder than it looks. Nope, that's too hard. On the whiteboard. 3 pi over 2. My y bottoms out at negative 1. We keep going. We've got root 2 over 2, negative root 2 over 2. We're back at the negative 0.7. And then at 2 pi, we're back to our y 0. So our curve curves up, down, down. There's our sine curve. Now, could I just keep spinning and it would repeat the process. So it's a periodic function and we can just keep going. Does this go on forever? Does it go backwards as well? Could I go this way? Can I have negative angles? 100%. So that, not really done really well as I continued. That's my sine curve. Okay? Starts at 0. Has a maximum value of 1. Back to 0. Low of -1. Back to 0. They're not lines, they're curves. I did have one student one year who enjoyed giving me this as the sine graph. I'll mark you wrong. It's a sine curve. You don't give me straight lines, okay? All right, let's do cosine. So exactly the same principle, but now as we walk around the unit circle, I'm going to take the x values because the cosine is the x. So this time at 0, I have a cosine value at 1. Pi over 4, we've got that 0.7, which is the root 2 over 2. I get to pi over 2, and my cosine is now at 0. I'll have my negative 0.7 because I've got a negative x value that's happening. So I come down to my negative 0.7. At pi, I've got my -1. I'm at the bottom. Come back up to my negative 0.7. 3 pi over 2, I'm back to 0. Pi over 7 and 1. Pi over 7, sorry, 0.7. So cosine starts high, goes down low, and comes back up. And again, just like sine, this can keep going and going. Did you notice anything about the values that I used for sine and cosine? Did I use the same numbers, just in a different order? So the sine and cosine graph are actually the exact same graph. They've just been shifted from each other. But I use the same numbers, they have the same shape. The big difference that you need to recognize, cosine will start at a high point, sine will start in the middle. Okay, so they're the same graph, few little different characteristics that are going to come up. So those are the new base graphs, and guess what we're going to do to them? Transformations! All right, here we go. Trig has a few different things that we need to know about it. If we look at the graph, y is equal to 2 sine theta, would you guys agree that based on what we know about transformations, the 2 represents a vertical stretch? So instead of my high point being 1, my high point is 2. Instead of my low point being 1, my low point is -2. Did anything else about that graph change? No. So what we are starting to see, the arc went higher, and we're now calling that the amplitude of the graph. We're starting to see the fluctuation off of 0. So the height from the center is called the amplitude of the graph. The amplitude of the graph is always the absolute value of A. It's a distance off the center, which is why when you talk about amplitude, it's always a positive value. So it's not just a vertical stretch. In trig, it's amplitude. So we're changing some of the terminology for trig. This graph is periodic, which means it has a certain pattern that will repeat over and over and over again. The length of time it takes to create one pattern is called the period of the graph. That's how long it takes, that's the period. And then the pattern repeats itself again and again. The basic period for sine and cosine is 2 pi. One rotation around the circle, right? It's all based on the unit circle. So, based on our knowledge of transformations, we can answer these questions. So compare the graphs given a domain between 0 and 2 pi. The graph y is equal to sine theta and y is equal to 3 sine theta. What is the 3 going to do? It's a vertical stretch. So is it going to change the domain of the graph if we're affecting it vertically? So I like to just say there's no change there. If I stretch it vertically, is it going to affect the period? Well, the period was a horizontal measurement, right? So there's going to be no change in the period. What about the range and the amplitude? Okay, those are y values, right? Now, let's do a prediction. My original graph, y is equal to sine theta. What was its range? Well, just think of unit circle. What was the highest y could be and what was the lowest y could be? Right. It oscillated between -1 and 1. I'm changing the wording that I'm using, oscillating. We could then say that this has an amplitude. How far did my base graph go up and down from the center? 1. So that's the amplitude of that graph. Let's make a prediction. What about 3 sine theta? Well, if I stretch the y's, are -1 and 1 both y's? So will I multiply those by 3? Makes sense to me. Will that affect the amplitude? Well, of course it is. If it's going as high as 3 and as low as -3, my amplitude will therefore be 3. Let's verify. Grab your graphing calculators. Let's graph this puppy. All right. First thing we need to acknowledge, are we in radians? Go into our mode, in radians, perfect. The only reason that I want to be in radians, ladies and gentlemen, is that's what it told me to be in. Okay, so I'm going off of the domain there. Okay, so let's compare. Y is equal to sine x, which is the same as theta, and y is equal to 3 sine x. Now, before you hit enter, we're going to have to make sure that our windows are adjusted for this, correct? So there's a handy little zoom function. If you hit Z trig, it'll accommodate your window and all of your parameters and everything for whatever mode you're in. So the fact that I'm in radians, it'll adjust for it. So I can see my original sine graph, and I can see my adjusted cosine graph. Now, it does say it only wants it between 0 and 2 pi. So if I wanted to see precisely what they want me to see, I could adjust the graph to fit that single period. But my predictions were true. High of 3, low of -3, representing the amplitude, the distance, and nothing else was affected. Fair enough? Look good? Awesome. All right. Cosine. We're changing the function. This one's cosine. If I go from cos theta to y is equal to -1/2 cos theta, before you jump in your calculators, is this going to change the domain? It's an a value, so does it affect the x values? No. A affects the y, no change in domain. Is this going to affect the period? Well, no. The period is a horizontal length, that's not going to change. Is this going to affect the range? Well, yeah, those affect the y values and amplitude. Let's get to some predictions. Cos. What was the range for cosine? How low could it go? How high could it go? Exactly the same as sine, right? -1 to 1. Meaning that it also had an amplitude of 1. Got as high as 1 and as low as -1. What's going to happen with -1/2 cos theta? What's going to be the range? Somebody said something.
1/2.
1/2?
To
Could I write 1/2 to -1/2? You're right with the numbers, but can I do them in that order?
No.
I have to do my smallest to biggest for interval notation, but your numbers were spot on. What's my amplitude? Makes sense. Can it be -1/2? No, it's a distance measurement. Amplitude can't be negative. All right, let's verify our findings. Cos x is our base graph. -1/2 cos x as my transformed graph. Went as high as 1/2, went as low as -1/2. Can you see the effect of the reflection? So instead of starting at 1, it started at -1. So all of our transformations are still in play, guys. They're exactly being used the way we think they are. All right, so notice vertical stretches work the same way that they always did. Remember, vertical stretches only affect what is going along the y. Vertical stretches, we can now say in trig, affect the amplitude and the range. Those are our two y parameters that they're going to affect. How'd that go? All right. Let's deal with b then. Oh, we have to beware of the b. Why do we beware of the b? Because isn't a stretch of 4 in that first one? No, it's a stretch of? Beautiful. So, let's take a look at this. We already agreed that that's a horizontal stretch of 1/4. So is that going to affect the domain? Possibly. But what is the domain of the sine graph? Does it go left and right forever? So if I horizontally stretch it, does my forever change? So in this case, it could have. We're cognizant that it affected the x, but my domain for this graph is forever. Period. Okay, well, that was a horizontal measurement, right? So this one's going to be affected. Range? No. Amplitude? No. Okay. What was the original period for sine? 2π, 1 rotation. When I do my transformed graph of 4 theta, how am I going to find it? Well, I'm going to take the original period, multiply it by the stretch, and reduce my fraction. I'm just applying the stretch in the same way that I always would have. Does that make sense? So I went from a period of 2π to a period of π/2. Let's check. So we have sine x and we have sine 4x. Okay, that makes sense. It looks like it came in like an accordion, right? So let's see here. Here's my red. As I go through it, when did it do 1 period? Well, if we take a look at our window, every tick is a π/2, and that actually hit on the very first tick. So we were completely correct in our predictions. Okay, all it did to pull it together, the period got reduced. Perfect. Yes?
What do you mean by tick?
When I look at this, it's a scale. So when I do the ticks along the graph,
Oh,
that scale is telling me what 1 tick represents. Okay. Do we need to prove it with the graph all the time now, or are you feeling pretty confident in your transformations? Yeah, math was done before graphing calculators. I like to keep reminding you guys. Okay, the domain kind of gets changed by this, but because it's infinite, no, not really. So we're going to say no change. We are starting to get this idea of a period as a horizontal measurement, so that will be affected. But range and amplitude don't move, because that b affects the x. All right, guys. Original period of cosine. Any different than sine? No. 1 rotation around the unit circle. Can you tell me, though, what the period of cos 1/2 theta is going to be? No. Because we took our base period, we multiplied it by the reciprocal. Watch that B. It's always a reciprocal. So this time it was a stretch of 2, so my period got longer and bigger, right? So that went from 2 pi doubled to 4 pi. Okay, horizontal stretches. Essentially, we're doing the same thing. Specifically in trig, they affect the period. Okay, the period of my graph is going to change, how often the pattern repeats. Now, we like to start to pull the reciprocal into a basic idea. Instead of saying it's 2 pi times 1 over b, they pull it nicely together. The period is 2 pi over b. They just they simplified it. You can do that in radians or degrees. It really doesn't matter. Okay, that's A and B. Feeling good? Let's sketch one without our calculators together. So let's start with things that we need to have. We take a look at the graph of y equals 4 cos 2x. State the amplitude and the period, because those are the main things I need to work with. So the amplitude is, good. The period is going to be, it asks me to work in radians. So I'm going to use the base period of 2 pi divided by my b value, and I get a period of pi. Now, using that information, I'm going to sketch the graph. So here's what's relevant. I need to know how high and how low this is going to go. So if I stretch this, the high point, the range is going to be between -4 and +4. Make sense? Okay. That allows me to know how high and low I'm going. I also know that I'm going to have a period of pi. So straight away that tells me, because this is the cosine graph, I'm going to start at the maximum and I'm going to end at the maximum. Does that make sense for cosine? So I'm going to start at 4 and I'm going to end at 4. I also know halfway between there, I'm going to be at the bottom of -1. So what's halfway between 0 and pi? Pi over 2. I'm going to be at the bottom. I've got some x-intercepts in there because if I'm going from a high of 4 to a low of -4, I'm crossing the axis. I'm crossing the axis halfway in between my high and my low. So what's halfway between 0 and pi over 2? Pi over 4. And now I need to find the halfway point between pi over 2 and pi for it to come back through. 3 pi over 4. So my first graphing, one period, is I start at my high, I go through my x-intercept, I bottom out, I cross, and I come back up. Now it wants me to graph between 0 and 2 pi. So how many periods am I going to have? 2. So I need to do that all again. So I think to myself, my period is going to happen in another pi. So I'm going to have a high point at 2 pi. Halfway, I'm going to bottom out, and that's happening at 3 pi. Oops, I jumped. 3 pi over 2. I jumped. Now I need to find halfway, and that starts to get a little fun. So I'm a pattern person. This is 1/4, this is 2/4, this is 3/4, this is 4/4. So next is going to be 5/4, 6/4, 7/4. And there are my x-intercepts. see if I can do this way. And there is the other period of my graph. So you see how I'm kind of taking key aspects and thinking about what's happening in between those key aspects? So there is my, not very good because I don't have a scale really, sketch of 4 cos 2x that I could verify in my graphing calculator. So does that make sense? So I'm taking the start points, starts and ends at the same point, then there's a middle, then there's x-intercepts, and all of those are halves of each other. What do you think? So bad?
I think we can verify.
You verified with a teacher who's brilliant, so it's good. Okay. Okay, here we go. I already said that sine and cosine are pretty much the same graph, right? So a lot of this is going to be repetitive. What's the maximum value of sine? Thank goodness you're here, Nick, I swear. What's the lowest value of sine? What about cosine? What's its highest value? Exactly the same. Same maxes and mins, doesn't matter. What about their amplitudes? Sine and cosine any different in terms of their amplitudes? And what is it? 1. Well, this seems pretty easy so far. What about their period? Is their period any different? What's their period? 2 pi. And yes, it could be 2 pi or 360 degrees, depending on how you were asked to discuss. Y-intercept. Well, they have a different y-intercept or the same? This one's different. Sine started at 0 and went up, down, up. So its y-intercept is 0 for sine. But where did cosine start? 1. It started at the maximum. So here's the first thing that's different. This is how they're out of phase. They have different start points. I'm going to come back to x-intercepts in a second because that's where all the difficulty is going to come. The domain. Can I keep spinning that arm forwards and backwards forever and ever? Is there any angle I can't put into sine or cosine? No. So the domain for both are unrestricted. Negative infinity to infinity, negative infinity to infinity. Well, if I already know the maximums and minimums, which are by definition y points, do I already know the range? I mean, this goes between -1 and 1, both of them. Okay, now we're ready to do the real work. X-intercepts. Let's take a look at sine first. Sine goes like this. First x-intercept is nice and easy to see, right? 0, 0. When does the next one happen? Pi. When does the next one happen? But because this can keep going on forever, when's the next one going to happen? Then? Okay, so would you agree this is happening every pi, these x-intercepts? So how do I make a general statement for all the x-intercepts possible? And what does n have to be? Beautiful. Oh, you guys are brilliant. Brilliant, I tells you. Now, I could have done this in degrees as well, but I'm so proud you guys went straight to radians. Warm my hearts. All for it. All right, cosine's going to be a little different though, isn't it? Sine's actually nice and easy. It's cosine that we really need to put on our thinking cap. And it sounds like you guys are already putting on your thinking caps. Okay. Where does my first x-intercept happen with cosine? Pi over 2. Where does the next one happen? 3 pi over 2. If I kept going, when would the next one happen? 5 pi over 2, then 7 pi over 2, then 9 pi over 2. Do you see how we're creating that pattern about what's happening? So now how am I going to represent this one for all x-intercepts? Well, would you agree we start at pi over 2? Would you also agree it's not happening every pi over 2? So I can't just put in. But how far apart are they happening? Pi. So I will add pi n times, but they must be integers. So that one's a little bit different because it didn't start at 0. I couldn't just put it as 1. I had to say it started here and then created the pattern of the same distance apart. So again, I could have said 90 degrees plus 180 degrees n NEI. But that's the pattern that's happening. So it's very patterned sinusoidal data. Are we good with everything except maybe the x-intercepts? Like we feel solid on everything but maybe the x-intercepts? Feeling okay? Okay. Let's start transforming them then. All right. Describe the transformations. Okay, because this is a non-diploma year, which I'm so happy about, we get to abbreviate. Would you agree with me this is a vertical stretch by a factor of 2? Would you agree with me this is a horizontal stretch by a factor of 1/4? It holds true just like chapter 1. Okay, nothing different there. What is the amplitude of this particular function? Well, I go to the a value. The amplitude is the absolute value of the a value, which meant I stretched my basic range that went from -1 to 1, and my range now goes from -2 to 2. We're going to do the period in degrees and radians. So I can think of it as a stretch. I can think of it as my period divided by b. So this is going to be 360 degrees divided by 4. The same thing as timesing by 1/4, which means that this is going to have a period of 90 degrees. Same thing would happen with the period in radians. You take your base period of 2 pi, divide it by the b value, and simplify your fraction. X-intercepts. So I'm dealing with a horizontal stretch factor. So is that going to affect my x-intercepts? Yeah. Or is it going to affect them all consistently in the exact same way? Okay. So I'm dealing with my sine intercepts. So if we go back and look, my sine intercepts are pi n NEI. So when I multiply that by 1/4, what's it going to become? Don't overcomplicate that one. It's going to be pi quarters n NEI. I just multiplied it by 1/4. That's it. Nothing really changes. Nice and straightforward. The y-intercept? Well, sine starts at the origin. So is it affected by any stretches at all? So it stays at 0, 0. Stretches are nice. They're fairly straightforward. They're nice and easy. Are we okay with this? This is normally the stumbling block right here. Okay. Try a cosine column. Work ahead of me a little bit. Most of this is straightforward. It's just going to be those x-intercepts. How are we doing so far? Straightforward, okay. I'm gonna do the y-intercept because it's easier and I can throw that up and make sure everybody's got that one correct. X-intercepts, now flip back. Look at what the x-intercepts were in the base graph and stretch them by a factor of 1/3. So the x-intercepts of cosine, we started at pi over 2 in the original. We multiply that by 1/3. So now that x-intercept started at pi over 6. Make sense? Then I would add pi n, but that's also stretched by a factor of 1/3. So now I'm going to add pi over 3n NEI. I just multiplied both things by 1/3. That's it. It's exactly what it looks like. There are zero tricks here as long as we understand the b value is a reciprocal stretch. That's it. Did you get all that? Oh, you're such a smart class. That's so awesome. Okay, try the next one. What is the negative going to do? What's the 6 going to do? I saw cosine in my head. Let's try that again. Did you get that? Make sense? It's not that hard, is it? Okay, we're just doing stretches over and over and over. All right, I believe you can do the next two without much support from me. It's repetitive, but we want to kind of hammer in those x-intercepts. But they're just stretches. last one, cosine always requires a little bit of extra thought. Sine is nice. It just flows. Cosine is always a little bit of a, let's stop and think. Pause here to make sure you do this thinking. So I'm looking at my original. I just multiply everything by 3. 3 pi over 2 plus 3 pi n e I. Stretches are easy. They do exactly what you think that they're going to do as long as you think about the b value being a reciprocal. Very straightforward. Okay. Start playing with some of the new terminology, period, amplitude. We've got new base graphs that start at different places. We need to be aware of the effects of the stretch on that. So why don't you guys work on that until about